Welcome to lecture number 6 on adaptive signal processing. In this video, I am going to discuss properties of autocorrelation matrix, capital R matrix. So here you see that in my previous lectures, we have discussed several applications of adaptive filters. But in this course, throughout the course, we'll consider one application, that is system identification problem. And this block diagram we have already considered for system identification problem. This omega naught is your unknown system filter coefficients, and Vn is the observation noise added with this unknown system. So when input is xn to this unknown system, then Dn is the corresponding output that we'll call as desired sequence Dn. So we'll try to estimate this W naught using one filter Wn. So Wn will try to update from this error En, where En is error between these two, Dn and Yn, and Yn is the output of our filter Wn vector. Okay, so here this is our unknown system. So this is the objective, to estimate this W naught. And already we have discussed how to estimate W naught in the best way on the optimum filter. So for optimum filter, Wiener filter, we have considered the cost function J as expected value of E square n. So this is called mean of square of errors. So mean square error. So we'll try to minimize this cost, mean square error, where En is this error between Dn and Yn. And Yn is the output of our filter that we can write in this way. This is the convolution process. W is the weight vector Wn at nth iteration, and Xn is the regressor vector. It will contain the samples of Xn, Xn minus 1, Xn minus 2, the past L samples if channel length is capital L. Okay. So we have already discussed this Wiener filter in previous lectures. So if you have some confusion, you can go through that lecture. So solution we have obtained in this way. The optimum filter W opt will be R inverse times P vector. So here this R is actually expected value of Xn and X transpose n. And this we will call as autocorrelation matrix. Okay, so in this lecture we are interested to explore the properties of this autocorrelation matrix R in detail. So here P is actually your cos correlation vector, the correlation between Dn, desired sequence, and Xn regressor vector. That expected value is your P vector. So if you multiply R inverse and P, we will get optimum filter, Wiener filter coefficients. Okay, so you understand this is your autocorrelation coefficient R, and we will try to find the properties of this R matrix. And you see, these properties of R matrix will play a big role to analyze adaptive algorithms. That will be discussed in subsequent lectures, and we'll see that all adaptive algorithms, including least mean square, NLMS, normalized least mean square, or recursive least square, RLS, everywhere, while you take some expected operator with this Wn or the variance, if you want to compute mean square error, you will find this R matrix, okay, in between. So the properties of R are important to understand. Then only you will be able to analyze those adaptive algorithms. Okay, so that's how we will discuss the properties of autocorrelation matrix in detail in this lecture. So actually, 2 lectures we'll consider to cover total all the properties of autocorrelation matrix. And you understand that the autocorrelation matrix are, if I consider the system length is capital L, means this regressor vector is length L cross 1. Okay, this is your vector, okay, column vector, xn regressor vector, starting from this one, xn, xn minus 1, xn minus 2, x of n minus L plus 1. This will call as regressor vector. Okay, then it transpose, obviously it will become a row vector. So xn basically a column vector and x transpose n is a row vector. So R matrix is expected value of xn and x transpose n. Okay, so this is the R matrix. So if we expand it, then we will find these elements. First element will be expected value of x square n, then expected value of xn, xn minus 1, then xn, xn minus 2, like that, up to expected value of xn, x of n minus L plus 1. This is the first row. Second row, similarly to start with x of n minus 1 will multiply with all xn, xn minus 1, xn minus 2, like that. So you will find that it is expected value of xn minus 1 times xn. Next one will be expected value of x squared n minus 1. The next one will be expected value of x of n minus 1 times x of n plus 1, like that. So last element in this row will become expected value of x of n minus 1 times expected value of x of n minus L plus 1. So in this way, this last element will become expected value of x square n minus L plus 1. So this is your autocorrelation matrix. Okay. And in our formulation, we will consider xn as a wide sense stationary sequence. Meaning is that its expected value of x square n is independent of n, doesn't depend on the sequence index n. It's a constant. That value is, we'll consider sigma x square. Similarly, the correlation between two samples, if they will differ by L length, L positions, so if one is x of m, other one is x of m plus minus L, the difference is L, then this autocorrelation, this correlation one expected value is again independent of m. It will depend on only the L, so that will call it RL. So with this form, if I consider RL equal to 0, then it is R of 0, of sub 0, that is same as sigma x squared, right? So we can use this wide sense stationary property of xn. Then we'll try to analyze the properties of R. Okay. So for this only, for this stationary wide sense stationary process only, we'll consider properties. Okay. Right. So we'll consider now properties of autocorrelation matrix. And I request all of you, if you have not subscribed this channel and if you want to understand adaptive algorithms in detail, please subscribe my channel. I'll be uploading all the subsequent lectures in this channel. Okay. Now, first property, that is, first one is this autocorrelation matrix R is symmetrical. So this is the one property, and we will try to prove this one. So we know understand that R is expected value of xn and x transpose n. We understand xn is a regressor vector com composed of those xn, xn minus 1, xn minus 2, all the past L sequences. Okay. Now, if I take transpose of this R, so R transpose, so we'll take a transpose of this one. So this is only operator, linear operator, expect operator E. It's outside. So we'll take the transpose of this one. Okay. Now we know that AB whole transpose we can write as B transpose times A transpose. Okay. So this property will use it. So this is A, this is B suppose. So this whole transpose A, B whole to the transpose, we can write B transpose, this transpose first, X transpose N, that transpose, and then this is your A, that transpose, X transpose N. Okay, so this is your B, so B transpose, this B is transpose, and this is your A, it's transpose, A transpose, right? And then now this A x to the power transpose again transpose. If you take 2 times transpose, then obviously you should get the same vector or matrix, right? So you are going to get this one as again xn because A transpose again transpose will become A. Okay, so now this is replaced by xn, and now you see this is again xn and x transpose n, that expect operator. So this is basically this one, and this is your actual autocorrelation matrix R. So it implies that the transpose of R matrix again it will become R, thus R is symmetrical. So columns and rows, if you interchange, you will get the same matrix. Okay. So this is one beautiful property of R matrix. The next one, R is 12-Lich matrix as well. Okay. So we understand these R as this one because that we have seen. It's expected value of x square n. Next one is xn, xn minus 1. The last one is xn, xn minus l plus 1. And similarly, second row, third row, and last row. Okay. And here we will use that wide chain stationary property of xn. So expected value of x square n is independent of index n. It is becoming x sigma x square, and correlation between sample m and m plus minus l is again independent of small m index. It just depends on the difference l. So it is function of l. That we will write as r of sub l. Okay. So if I replace this one, so here you see this is square terms. All square terms should be replaced by sigma x squared. So this one is sigma x squared. We can replace. This is also sigma x squared. This is also sigma x squared. So all these diagonal terms are sigma x squared. That we can replace. And you see this one, there is only one sample difference. So that this one we can write R1. Similarly, its adjacent, it's R1. Its adjacent left side also R1. So all adjacents along these diagonals are R1, both sides, right side or left side, both sides. Okay. Similarly, the next to next. Okay. So the third element will be R2. Similarly, here also you will get fourth element will be R2. So third row, fifth element will be R2, like that. So you see, this diagonal terms is becoming sigma x square, and next to this one, this diagonal of this one, this line along this one, all are adjacent to this line. So obviously this is R1, this is R1, all R1. Then it is R2, then it is R3, and last one is R of L minus 1. Similarly, this side as well. This is R1, then R2, then R of L minus 1. So this, if this is true, then this type of matrix is called 12-Lich matrix. Okay, so R is twelve-link matrix, right? Next property, third one, I'll consider this R is non-negative definite matrix, or it is also called positive semi-definite matrix. So what is the meaning of positive semi-definite matrix, right? So definition is that if A is a matrix, a square matrix n cross n, okay, dimension n by n, then this A matrix will be called positive semi-definite matrix if I consider any vector u for all the vector, not only the u is a vector n cross 1, then if you multiply u transpose a u, and remember u is a column vector, A is a matrix, and u transpose will be row vector, so this will become a scalar quantity, and this scalar quantity value, because this dimension is 1 cross n cross n, and n cross 1, so this product will become 1 cross 1 scalar quantity, right? And that value is more than equal to 0. So this equal, because of this equal sign, it is called semi-definite matrix, positive because it is positive side, okay, always positive value. So positive semi-definite matrix, or it is also called non-negative, it is never negative, and definite matrix. So it's not less than 0, right? So this is the definition of positive semi-definite matrix, and our claim is that R is such positive semi-definite matrix. We want to prove this one. Now, to prove this, what will consider? First, we will consider again that xn, suppose a sequence of a system input sequence xn, right? This is our input sequence, and from that input sequence, we can make our regressor vector, input regressor vector, this column vector xn, x of n minus 1 up to x of n minus capital N plus 1. Here I have considered system length is capital N. Okay, so for this n system length, the regressive vector dimension should be n cross 1. Okay, it's a column vector, right? Now we'll consider this one, that yn equals to u transpose xn, and u is one constant vector. Okay, it is not varying over time, but any constant n cross 1 vector. Okay, so if it is so, so this one we can understand. So this type of equation we have already obtained, yn equals to u transpose xn. So actually this we can realize as in system point of view, signal system point of view, where xn is the input sequence and output sequence is yn, and un is impulse response. So you see, so this one we can consider xn is the input sequence, and we can consider one system with the impulse response un. This is a vector, the sequence vector. Okay, then yn will become the output. So this output is basically convolution between this system sequence and input sequence, that we can rewrite as u transpose xn if the system is FIR. So already I have said that this u is one finite length column vector n cross 1. Thus in this model it's a FIR system. So we can write as yn equals to u transpose xn. So this is the interpretation of that equation, right? So we understand if xn is input sequence and yn is the corresponding output sequence for this system, right? Now, if we want to find out the energy of this sequence yn, expected value of y square n, right? So this yn we can write this yn times again yn, and so this yn again we can rewrite it as this way, right? So this one is right. So what we'll do, this xn, we can write this is dot product. So again we can write x transpose n times u, right? So first one is again, this is your yn, this also yn. I want to make y square. We'll multiply these two times, but first time we'll write in this way, u transpose xn. Second time we'll write x transpose n un, u. Okay. So many times we will use this type of formulation. Now if we take expected operator, remember u is constant vector, and this is only random, its content random variables xn because of vectors. Okay. So this one we can write outside, u transpose, this one I can take outside, this u also I can take outside, only I can take this expected operator here only, xn and x transpose n, right? And we understand that this is actually autocorrelation matrix R. Thus this will become u transpose R and u, right? So this is expected value of y square n is actually u transpose R u. And now, as this is the energy of this output sequence, it is always more than 0, right? So this is more than 0, equal to 0. So if system is 0, then only output is 0, or input is 0, then also output could be 0, right? So we can put equal sign here also, more than equal to 0. So as this is more than equal to 0 and this one is same, so obviously this term u transpose R u will be more than equal to 0. And that is the definition of positive semi-definite matrix. Thus R is positive semi-definite matrix. This is proved. Okay. So this is the third property of autocorrelation matrix R. Next property, that is eigenvalues of R. So we can find several eigenvalues. So we'll try to investigate the nature of these eigenvalues. And this property says that eigenvalues of R are always non-negative and real. Okay, this is an important property because it will show some characteristics of eigenvalues. So we'll also see the characteristics of eigenvectors later. So we'll try to prove this one, that eigenvalues of R matrix are always non-negative and real. Now consider that lambda I is one such eigenvalue of R and the corresponding eigenvector is your Qy, right? Now next one is, so because of lambda I is the eigenvalues and corresponding eigenvector is Qy, so if I multiply R times Qy, Qy is the eigenvector, so you will get the same vector Qy multiplied by its eigenvalue. Okay, corresponding eigenvalue. So this is the basically equation for eigenvalue and eigenvector relation, right? So we'll start from here only. Now we'll consider this one, this Qy transpose R Qy, because already in the third property we have seen that for any vector u transpose R u, that is always more than equal to 0 because R is positive semi-definite matrix that we can use here. Okay, so you see this Qy transpose R Qy, so this R Qy already we have seen here, lambda I times Qy, so that we can replace. So this R Qy you can replace lambda times Qy. Now lambda is your constant, scalar constant. So that I can take outside, and qi is a vector. So lambda is outside. This is qi transpose times qi. So this is your qi is a column vector. It transpose will become a row vector. This is row vector times column vector. You will get 1 cross 1 element, the scalar quantity, and that is your norm2 square. Okay, so qi norm2 square. So you will take square of each element and sum it up. You will get norm2 square, right? Now, so this is your lambda I times qi norm2 square equals to qi transpose r qi. And we understand that this is always positive or equal to 0, semi-definite, positive semi-definite matrix. Okay, so this is always positive or equal to 0 as R is positive semi-definite matrix by property number 3. So if this is positive more than 0, and now this norm square is always positive or equal to 0. Norm is always positive equal to 0. So this is positive and real. This is also real positive. So obviously this lambda I should be real and more than equal to 0. Right? Thus, the eigenvalue, any eigenvalue of R matrix, they are non-negative. They cannot be negative. At most, it could be 0, minimum is 0, or is positive, and always it is real. Okay. So this is important, very, very important property. And we'll discuss the eigenvectors of R matrix, and then eigenvalue decomposition of R matrix and other things of this orthogonal matrix R. So those properties will be discussed in the next lecture. So now for this lecture, the summary is like this. This is your orthogonal matrix R. R is expected value of xn and x transpose n. And for this R orthogonal matrix, R is symmetrical. First property. Second property, R is 12H matrix. Third property is R is non-negative definite matrix, or it is called positive semi-definite matrix. Meaning is that U transpose R U, that is always more than equal to 0. And fourth property we have considered here, the eigenvalues of R are always non-negative and real. Okay. So next video will discuss eigenvectors of R matrix and corresponding relations. So another 3 properties of R matrix we will be discussing in the next video. So please keep watching these videos. And if you enjoy this video, you can subscribe this channel. For subscription, you will press the subscription button first, and then don't forget to press bell button. Then only you will get immediate notification of my future videos. I hope you are going to subscribe my channel. If you have not done yet, I'll be uploading all the videos in this channel. So keep watching. Thank you.